part 14 of my book, Causation and the Universe, a bridge between the 1900s and the 2000s, by me, Roger Michael Klang. And that's me in the image. GNZ11 is a high redshift galaxy found in the constellation Ursa Major. The discovery of this galaxy was published in a paper headed by P.A. Osh and Gabriel Brammer, Cosmic Dawn Center. GNZ11 is the oldest and most distant known galaxy yet identified in the observable universe, having a spectroscopic redshift of Z equals 11.09, which is considered to correspond to a proper distance of approximately 32 billion light years. They say it is observed as it existed 13.4 billion years ago, just 400 million years after the Big Bang. Except look at the image below and convince yourself that the galaxy expands correspondingly with the Earth. Someone measured the galaxy's redshift and concluded that the distance from Earth to this galaxy is, allegedly, 32 billion light years. 97% of the galaxies in the universe are said to move away from us at a greater speed than 300,000 kilometers per second. The galaxies that don't move away from us at a speed greater than the speed of light are said to be within the Hubble sphere, which is 14 billion light years in radius, with our Sun in the middle. Except the idea that galaxies move away from us at a greater speed than the speed of light is utter nonsense. Light travels at 300,000 kilometers per second, if measured by any observer in the universe, always, wherever an observer is located, and if ever two objects are moving away from or toward one another. The speed of light in vacuum is constant, as demonstrated in numerous experiments. Period. That's where I think that the physics community is correct. But apparently, the physics community itself isn't in agreement. Otherwise, we wouldn't see the GNZ11 at all, because it would rip apart the space-time continuum. I think the physics community people must rethink the whole concept about the alleged constituents of the universe, instead of concluding that the measured redshift in 97% of the observable matter in the universe would mean that this matter is moving away from us at a greater speed than the speed of light. Still, they can measure this light. Enter the Pythagorean theorem for right-angled triangles. A squared plus b squared equals c squared. Let us slap the Pythagorean theorem onto the universe. In the image above, objects A and B separate from each other in a 90 degrees angle at a speed well below the speed of light. The distance to the allegedly ascertained beginning of the universe is 13 billion light years for both object A and object B. The distance between object A and object B is then 18 billion light years. For the GNZ11 to be 32 billion light years apart from our galaxy must be 23 billion light years old. That is if we had been located at the edge of the universe, as well as the GNZ11 had been located at the other edge. Obviously, we are not located at the edge of the visible universe. Since most of the objects in the universe have a velocity well below the speed of light, we should expect the universe to be much, much older than 13 or perhaps 23 billion light years of age. 32 billion light years is how far we to date can see, given that we are correct in our assessment of the distance from our galaxy to the GNZ11. Object A and object B in the image above have always been within sight of one another since the early universe. The luminosity from the origin of the universe has long since surpassed us, since light travels at 300,000 kilometers per second. Say that most of the galaxies in the known universe have a velocity of about 67 kilometers per second. So if the assessment for the expansion speed is correct, then the age of the universe must be more than 300,000 kilometers per second divided with 67 kilometers per second is roughly equal to 4,478 times larger. Because it would take 4,478 times longer for object B in the image above to reach a distance from Earth where we can detect object B at a 32 billion light year distance, based on object B's redshift. Most of the emitted light from object B that we can see have long since surpassed us here on Earth. Only light leaving object B at approximately 32 billion light years ago is visible to us. 23 billion light years times 4,478 is roughly equal to 100 trillion years old, but supposedly more like double, unless there was inflation. Light year is a yardstick, but also an age. If the scale of the universe is 100 trillion years of age, or rather twice that, this would explain why the universe's galaxies are not noticeably more densely packed the further back in time we look from Hubble and James Webb. With the aid of telescopes, we can see only a fraction of the universe. It would also explain why megastructure formation of galaxies like the Big Ring and the Giant Arc can have developed in our universe. They had time. I have imaginary set up the calculation according to the Pythagorean theorem for a right-angled triangle, i.e. a squared plus b squared equals c squared, and then calculated the square root of c squared to get the horizontal distance between object A and object B in the image above. That is why I don't think there is a real breakthrough in finding out the shape of the universe by cosmologists. Because the scale of the universe is so enormous, it's just not possible to assess what shape the universe has got by using their methods. Their proposal is that we can find out the geometry and ultimately topology of the universe by observing the universe in its largest scales possible with our available means. Excuse me. It is not achievable even when using the cosmic microwave background and its 93 billion light year cross stretch, with us in the middle. I am postulating that the sheer scale of the universe make it virtually impossible to come to any other conclusion than that our universe is a flat universe, whether that is the case or not. For massive object scales, space can be curved, so it should allegedly be possible for the universe to be finitely closed, curved. There are three basic geometric shapes: spherical, round, Euclidean, flat, and hyperbolic, Pringles inwardly shaped. Draw a triangle on any one of them, and the result will differ, depending on which geometric shape you are using for the purpose. On a spherical shape, the three angles will add up to more than 180 degrees. On an inwardly hyperbolic shape, the angles will add up to less than 180 degrees. On a spherical shaped object, parallel lines will eventually converge. On a hyperbolic inwardly shaped object, parallel lines will diverge. However, if the universe is something like more than 100 trillion years of age, how can we hope to measure the universe by looking at CMB radiation, which is only 93 billion light years distant, or even half of that? I also think that a universe with some sort of sophisticated finite topology, like a torus, donut, or a Mobius strip, or a Klang bottle, or really most of all, the all-in-all 18 topology shapes the universe can be shaped like, may just slightly complicate the origin of that universe. I mean, it is virtually impossible to ever explain an expanding finite universe shaped like a Klein bottle or even a torus. Two questions come to mind, not even considering the often expressed difficult unanswered questions of why and how our universe emerged from what appears as a singularity. Where did it origin? What force or law of nature is behind the very oddly developing topology of such a universe?